All right, so let's go ahead and get started. So is there anybody here who does not have access to the Linux server yet? Hopefully that's all been squared away. Hopefully everybody was able to figure out how to do the one-day assignments. 202 posted this morning at 8 o'clock. We're going to go over that in a few minutes. But I want to start by going over some C, possibly review, talking about structures and typedefs and how to use a structure. And then we'll talk about the new one-day assignment 202, which is due tomorrow morning. And then we'll jump into PA1 and we'll talk more about linked lists. And we'll go through that assignment in detail. Any questions before we get started on all of that?
How are you?
I'm well, thank you. All right, so in any programming language, if you have multiple pieces of information, for example, in 222, you were making a dictionary of how many times certain phrases occurred in some input. And you had two pieces of information. You had a collection of phrases and a collection of counts. So phrase 1 occurred this many times, phrase 2 occurred that many times, and so on. That's something that's sometimes called parallel arrays, right? And it's a fine way to store information, but if you have 15 pieces of information that's all associated with each other, you end up with 15 parallel arrays. So the idea of a structure is basically to take multiple pieces of information, combine them into a single thing. And so in C, there's a statement called struct. And the syntax is struct, that's a keyword, followed by the name of the structure. And the name can be pretty much anything reasonable, possibly anything, but don't do something weird like, you know, space asterisk or something. But a reasonable name. So what should we call our structure? Give me a name.
Name.
Say again?
Name.
Name, okay, so structure, name. And then curly brackets and a semicolon at the end. And inside here in this definition between the brackets, we can list a bunch of variables. And they can be any types of variables. They can have any names that we want. So for example, we might have an integer x. We might have a character c. We might have an integer array called stuff, which holds 10 integers. And we might have a double, which we call x2. Hopefully your variable names would be more meaningful than xc stuff and x2, but I don't want to use names and make you think that the names are somehow significant, right? So the idea is struct name is a new type of variable, right? We know about ints and characters and doubles. Now we have a new type of variable called a structure name. And a structure name contains an integer, a character, an array of 10 integers, and a double. And if we want to create a variable of type structure name, it's just like declaring an integer, but instead of saying int variable, we say struct name, and then our variable. Let me just call it var. And so var is a variable that has 4 pieces to it. It contains inside itself an integer, a character, an array, and a double. And so if we were doing this in our 224 assignment where we had a dictionary of phrases and the number of times it occurred, our structure might be called, you know, phrase, and it would have 2 pieces. A string, a character array that contains the actual phrase, and then an integer that says how many times did that phrase occur. And we could make an array of those structured phrases, and that one array would contain the list of phrases and the list of occurrence counts. Okay, so I've declared a structure name called variable, and variable has all these 4 pieces to it. If I want to get to the x piece, the syntax is just var period x. So I can say var period x equals 17, and that sets the x piece of that structure to 17. And I can get to the character piece exactly the same way. Var character C equals, and whatever character you want. And if I want to get to this array called stuff, it's just var period stuff. And keep in mind that this var period stuff is just that name stuff, right? So if I want to find the fifth element in this array, I could say var period stuff bracket 5. And that would be the fifth element of this integer array called stuff. If I had a character array and I wanted to do a printf on it, I could say var period whatever the name of that character array is, right? Just as if I had said character array bracket 120. So var period some field, right, is basically whatever that field is. An integer, a character, an array of integers, a double, and so on. Is that clear? Right, so anytime we do stuff like this, write some junk code. I know I misspelled it. It's early. Stuff 10 double x2. Alright, so these things, xc, stuff x2, these are called fields. It's a term we'll use the rest of our lives. So those are fields, and if I want to make a variable of this type, I can say struct name var. And then I can assign a value. And I can make a loop where I assign values to all 10 elements of r.stuff, and I'm just setting them equal to the square of the index for no particular reason. And you can pass these to functions in the way that you would hopefully, that you would hope the compiler would expect. So I can say something like my function var. And let's just end right there. So my prototype for my function, I'm not going to use any return value, so I'm going to declare it to return a void. The name is my function, and the argument is a struct name. And I'll just call the argument A. So my function takes a struct name, and let's go ahead and write my function. And we're just going to print some stuff out here. Alright, so we'll just print out the value of the x field by printing out a.x. And we'll just print out the array. Whatever we call our array stuff. So we'll go through a loop and we'll take each element of a dot stuff from 1 through 10 or 0 through 9 and we'll print that out just to verify that we actually passed all this stuff by simply passing this this one argument to our function. Make sense what we're doing here? Okay. So, barring syntax errors, of which I have many. I forgot a semicolon somewhere. Oh. So in general, you're going to declare functions outside of, you're going to declare structures outside of functions. If I declare it in main, then only main knows about it. Yeah?
So would accessing elements in an array of structures look the same way with the period?
Yes. Yeah.
You would have like the ref and then the period.
So like this. Right, so a dot stuff is an array, and so a dot stuff bracket I is the ith element of that array. Is that what you're asking about?
Well, not like an element, array of structures.
Oh, an array of structures, yeah, exactly the same.
Okay.
Yeah. So array name, bracket, index, and that becomes a struct, so then you can say dot field name. Yep.
So is structure then a global variable?
It's not a variable, but it is kind of a global definition within this file, which is okay, right? Just like integer is sort of global. But I have no global variables in this file, right? I simply have a definition, kind of like a prototype. When I do my prototype up here, everywhere from this point on down knows what my function is, okay? Same idea here. From this point on down, everything knows what a struct name is. And that's usually what you want to have happen. All right. This is not my day for writing. See, no matter what I do, I get 4 errors. I don't know what, oh. Think of it as a Monday. This is my Monday. Alright, so you can't use struct name until you've declared struct name. So I was trying to use it at the top before I actually declared what a struct name was. Alright, that's better. So go ahead and run S, and it does what you'd hope, right? It prints out the value that we assigned to X and the value we assigned to all 10 elements of the array. So like I said, barring syntax errors and silly things, pretty straightforward to use, right? Okay, so we can also do a typedef. So if we have a structure named name, every time that we want to use this, we have to say struct name, struct name, struct name, and it gets kind of quirky looking. So we can define a new type. We can say typedef. And we can say what type we want to rename. So there's a struct name. And we can give it some shorter name that we like. So I don't know what we should call it. We could just call it name. And then instead of saying struct name, I can just say whatever my typedef was. Case should matter everywhere in C, as far as I know.
If you say struct name, all lowercase both times, would it give an error or something? Or would it accept that?
If you said what?
If you say struct name, both of them are the same name.
Oh, I think it'll be okay. Well, let's try that first. Right, so that's fine because variables are different from types. Just like I think you can say. I don't know if it'll let you do that. Can't do that. But you can do it with structs. Okay, so let's do a typedef. I'll call it an uppercase name just so it's clear what we're doing. So now uppercase name is a synonym for struct name. So down here, instead of saying struct name, I can say this takes an argument of type name with an uppercase N. And down here, instead of declaring var to be a struct name, I can declare it to be an uppercase name. And same thing down here. So typedefs don't do anything that you can't do just by typing out struct name, right? But it's a convenience. And it's pretty easy to forget to type the word struct. And it's one of these things where if you declare a variable to be, a name instead of a struct name, you're going to get 1,000 compile errors. So it's cleaner sometimes to use typedefs to give yourself a pseudonym for your structure, but you don't have to. Okay, and let's just go ahead and do arrays. Okay, now I've got an array of 100 of these struct names. And I can pick an index. Alright, so now I'm just manipulating and examining one element of this array. But var bracket 0 is a struct name. And so it has a field X, it has a field C, it has a field stuff, which is itself an array. And so things like this are perfectly logical.
Could it be a two-dimensional array?
Could be a two-dimensional array. And it will be things far hairier than that pretty soon. Which is glorious. Alright, so any questions on any of that?
Class has the quantity array to the function.
Yes. And that's what we're going to do most of the course, is pass pointers to structures. But I'm going to leave that for a little bit, but it works basically the same way. There's some shortcuts we can use when we're dealing with pointers to structures, though. That's where the dash greater than arrows thing comes in. Yeah. All right, any other questions on this? All right, so ODP 202, arrays of structures. Surprise. So you're going to define a structure. I need you to name your structure node, N-O-D-E lowercase, containing 3 fields, data, next, and valid. Data is an integer, next is an integer, valid is an integer. You have to define them in this order. Okay, I don't have that here, but on Canvas it highlights that. So data, next, valid. And I want you to write a function called init. And init does the following. It takes an array of nodes, and it assumes that there's 100 elements in that array, and it just does the following initialization. It sets element 0s valid to 1, data to 42, next to -1, and all the other elements set the valid to 0, data to 999, and next to -99999. Okay, the test bed is main 202. That's right on Canvas. It's just an old README. So the test bed is main 202 /temp. So write your function. Go ahead and write some test code to double check it, right? Just make an array of structures, call your init function, and then just do a loop and print out the values for element 0 and maybe elements 1 and 99. And just make sure that it seems to be doing the right thing. And then you're going to go ahead and you're going to assess it. So so you can compile it into an executable test bed by saying something like this, gcc-o. I'm calling it main202 just to keep it separate from the previous main. And then the name of the test bed, temp main202.o, and then the name of the file that you wrote containing your function, typically init.c. And then assess main202 and init.c. All right, so I've got my version of init.c. I bet I didn't put main202 in there. Okay. Close your eyes. Okay, open your eyes. All right, so compile your test bed and then assess it. Close your eyes. Okay. All right, so go into your assessment. It should say ODP202 initialization of an array of structs, and then use the G command. And there's a single test, so you should get 10 out of 10 on that. And then just exit out and you're good to go. So that's all set up and working on the server. I just didn't set it up on here all the way. Does that make sense? All right, so run that through before 8 o'clock tomorrow morning. So let's look at PA1. So PA1, you're going to do two things. You're going to write the code to implement a linked list, which we started talking about yesterday. We've still got to go through that in more careful detail. But you're going to write a set of functions for interacting with a linked list. And then you're going to write a main program that lets the user type in commands while the program's running and add things to a list, delete things from a list, print out a list, search for things in a list. Okay, this is what most of your programs are going to look like this quarter. You're going to implement some code, and then you're going to make a main program that lets the user type in commands that basically exercises the code. So let me show you what this looks like when it runs. So I run my main program, it gives me a prompt, okay, greater than with a blinking cursor means it's waiting for me to do something. If I don't know what to do, I can type a question mark, and it shows me my options. So I have 5 commands available. I can say I space followed by an integer that says add this number to the list, insert it. Okay, and it's inserting into a sorted list. I can say P, which says print out the list. I can search for a number, I can delete a number, or I can exit the program. So we start off with an empty list. If I say print, it doesn't print anything. If I search for something, there's nothing in there. If I try to delete something, there's nothing in the list. The list is totally empty right now. So let's insert some things. So give me a number. 12. Okay, so now if I print my list, it's got a 12 in it. Give me another number.
1 billion.
1 billion. Okay, so now if I print my list, I've got two numbers, 12 and a billion. Give me another number.
3.
3, good. Give me another.
-9.
-5. Did you say -9? All right, so now my list contains 5 things: -9, -5, 3, 12, and a billion. And it's sorted, right? It's always sorted. And we're not sorting the list per se. When we insert something, we're putting it in the right spot. If I say insert 8, it's actually going to update the list so that node 3 points to 8, which points to 12. And so when I print, I just print the nodes in the order that they're stored, and it's always sorted.
One more number. Number 3 again.
So if you try to insert something that's already in there, it should tell you it's already in the list. You can have a linked list with multiple occurrences of the same thing. I'm just doing this just as something else to do. Okay. So we can insert things into the list. And with this implementation, you can only store 100 things, 99 things in your list actually. So your insert code is going to make sure you don't run out of space. If you happen to run out of space, you can print out of space. But I probably won't test that. So we can insert, we can print, we can search. So we can say, is the number 3 in our list? Yes, it is. Is the number 4 in our list? No. Okay, we can delete things from our list. So if we want to delete that 8, we can say D8. And now when we print, the 8 is gone. And if I try to delete 8 now, it says it's not found. If I try to delete 4, it's not found. If I delete 1 billion, that's successful, and 1 billion is gone. And then when you hit an X, it exits the program. Okay, so that's your intended behavior of PA1. It's all about how you implement this, though. Okay, and all of the details in the assignment are about how I want you to implement this, what functions I want you to write, and how I want you to manipulate the list. While we're here, edge cases to check. Okay, typically the kinds of things that I will check when I'm testing your code. Print an empty list, delete from an empty list, search from an empty list. Right, empty lists are a special case. Print a single node, search a single node successfully and unsuccessfully, delete from a single node unsuccessfully and successfully, and print. Right, a single entry in your list is an edge case, because most of our code starts with the first node and goes until the last node. If there's only one node, sometimes your code is doing something special, right? And I would say in some cases having 2 nodes is an edge case also. If your code works for 3 nodes or more, it's probably going to work for 10 or 15 nodes also. Having stuff in your list, deleting all the stuff in the list, and then trying to insert stuff into that empty list again, that's an edge case. So you don't want to just, insert 3, insert 4, hey, it works, I'm done, turn it in. Okay? You really, really want to spend some time trying to break your program. Okay? Because that's effectively what I'm doing. I'm not trying to break it, but that's effectively what ends up happening, right? I'm trying different cases that will exercise how defensively you've programmed different pieces of it. Error checking, I'm not too concerned with error checking this quarter, okay? But basic things, if you say insert haha, that's not valid. Don't just take haha as a 0 and insert a 0, okay? If someone says insert haha, that's an error. Print out an error, don't insert anything. If someone says delete and doesn't say what they wanted to delete, don't delete some random number just because A to I gave you back a 0 or something, right? Notice they didn't give you an integer and say, hey, here's what you're supposed to type, right? Same thing if they delete haha. Don't delete something at random. Give them an error message. But things like this, if you're going to catch this as an error, that's going to take a lot of extra work. So again, my rule is if scanf sees this as I followed by an integer, you can take it as I followed by an integer and just go ahead and take it as an insert 12. Okay, so So that's all explained in the description of the program. All right, so details. So the ODPs are going to parallel the pieces of this for a while, right? Obviously, your next ODP is making an array of structures that happen to have 3 fields called data, valid, and next, right? Which, hey, coincidence. So the ODPs will help you sort of build up to this. All right, so that's your structure of a node. And you're going to make an array of these, and that's going to be that table that we were playing with yesterday when we were making linked lists. Okay, I want you to define a symbol called myNull and set that equal to -1. So when we were making the table, I said we'll put a special value to point to the next field if it doesn't exist. If we're at the last node, I was putting in the word null, okay? I want you to put in the word myNull, because null is a reserved word. And I want you to set myNull equal to -1. So, quick refresher, here's our array. It's got data, next, and valid. And the idea was whatever value is in here, that's the index of the next node in our list. And so we need a way to say, hey, there is no next node. This is the end of the list. And if we use a 0 or a 1 or a 999, we can't tell if that's a flag saying we're at the end of the list or if that's actually the location of the next entry in the list. So we use a negative number because there is no -1 element, right? There is no element bracket -1. So we're going to use a -1 to say end of the list. But don't use -1, use myNull. And if you don't remember the define statement, right, number sign define myNull -1 says when I say myNull, I mean -1. And the compiler, the preprocessor actually, will substitute myNull with -1. So it works exactly the same as if you say -1, but we're going to want to change this in PA2. We're not going to want it to be -1. So use a define statement. All right, and then declare your array struct node list bracket 100. And if you want to use a typedef, you can use the name of your typedef, list bracket 100. So list is your linked list, and it can contain 100 entries. All right, I've already given you like several lines of your code, so there's almost nothing left for you to write. Okay, except for all of these functions. So you want to write a function called init. It's going to be very similar to ODP's init, but slightly different. So init will take a struct node. Oh, I do have pointers here. Okay, we got to talk about pointers to struct nodes. We'll talk about that next. You're going to take a pointer to a struct node. And at index 0, you're going to set the next field to myNull. And you should clear the valid flag in all of the elements. So this third piece, valid, typically we're going to use 0 to say it's not valid. It means it's not in use. And if it is in use, we'll set it to a 1. So your init does two things, right? It takes the first entry in the array, sets the next field to myNull, and then it sets all the valid flags to 0. Where
The structure.
I was calling it LL for linked list. All right, so that's the init function, right? It just puts initial values into the array. The add function takes a struct node pointer and an integer, and it inserts the integer into the linked list. Okay, we'll work through some pictures in a bit to see how to do that, but we did that a bit yesterday. So that's what the add function does. The print function starts with the first node, follows through from pointer to pointer from one element of the list to the next, and it just prints out the data values. So it gives you a printout of all the entries in your list side by side, space in between. Delete does the obvious thing, it deletes the number that you pass to it. So it looks through the list, tries to find that number. If it finds it, it removes it. It returns a 1 if it deletes a node successfully, 0 if it didn't find the node. Okay, add returns 1 if it was successful, 0 if it was not successful. Search takes a struct node pointer and a number, and it searches for that number in the list. Returns a 1 if it's found, 0 if it's not found. So this represents an interface to your linked list code. Right? Your main program should just use these functions to do what it's trying to do. When the user says I space 5, you should take the number, you should notice that there was an I, so they're asking you to insert. You should find the number 5, use an scanf to convert it to an integer. And then you probably want to do a search. Search your linked list for the number 5. If it's already in there, print out number's already in the list. If 5 is not in there, then you call the add routine. Pass it the linked list, pass it the number 5, get the result back. If the result is 1, you can say success. If the result is 0, you can say we're out of space. If the user says D space 17, you notice there's a D, go ahead and call the delete function. Pass it the number 17, look at the return value. If it's 1, say success. If it's a 0, say 17 wasn't in the list. So this is a theme that's going to be prevalent throughout this quarter and next quarter, this idea of an interface to a data structure. Okay, a linked list is a data structure. It's a way of organizing and manipulating data. This is our interface to it. Your main program uses these functions to do everything it wants to do with that data structure.
Do you have a preference as to whether they're in separate files or in the main program?
Totally up to you. So since you're writing the main program and you're writing these things, you know, for example, that you know, this is the way that your linked list is stored. And so if you wanted to know in your main program, the person says insert something, and you want to say, oh, is there space to insert? You could write a for loop from 0 through 99 and check all these valid flags and make sure there's at least one valid flag that's a 0. Meaning that your list is not completely full. And if there's not, if all these valid flags are 1, your main program might say, sorry, there's no space in the array. Do not do that. Okay? Your main program should not know about this. It should not know about the valid flags. It should not know what the 1 and the 0 means, and that this is pointing to that, and so on. Nothing in your main program should depend on that. Your main program just uses these functions to interact with the data structure. Okay, this is one of the primary lessons from PA1, because it's going to be absolutely critical in everything we do. And this is something that we sometimes call an abstract data type. So an abstract data type is the idea that a linked list is a collection of data which we can initialize, we can insert things, we can print the contents, we can delete things, we can search for things. And that's it.
Could we make it so that when you invalidate a node, you also find because we don't care what order they're stored in the array anymore, that's the linked
Correct.
list. So to check and see if we have available data to make that easier when we delete, would it work to say, like, take that node and then count backwards from 99, and then the first valid one you find, flip them. And then when you check to see if there's any valid, just start with 99. If there's not a 0 at 99, you're full.
So that would make it faster to do this searching?
Well, because you'd be searching from the end, you wouldn't be going from 0 to 99.
You could do that, as long as you're doing that inside your delete or your insert or your search functions, yeah.
But that doesn't, like, that, I mean, my understanding of the node is right. It doesn't matter. You can flip on any which way you want during a search, insert, or whatever.
Yeah.
All that matters is where it's pointing.
Yeah. Okay. So the actual layout, right, this could be the first element of my list, this could be the second, this could be my third, this could be my fourth, this could be my fifth, right? Nothing wrong with that. And inside your code that implements the linked list, you might have reasons to rearrange those things, right? If it was a very big list and it pointed from here to there to there to the next planet over and back to here, right? You may want to gather those things up and bring them closer to each other periodically for the sake of cache efficiency. So you can do things like that. Just don't do it from your main program. All right, so this is the idea of an abstract data type, right, ADT. And part of the reason why I want you to do this is because for PA2 you can use exactly the same main program. You just link it to a new set of functions. Okay, so you may want to put your main program in a separate file, and then you could put all of these into one file called, linklist1.c or something. Or you can go crazy and put each function in a separate file. It's up to you. But PA2, you can probably use exactly the same main program and just call a different set of functions. All right, so we'll go back to implementation details in a minute. Main program, so you only use the above routines. First thing you do is call the initialize routine to make an empty linked list. Print out a prompt. Okay, I'm going to ask you not to clear the screen, not to put in sleep statements to show me, one message every 5 seconds, things like that. Let's stick to as close to the description as possible. So beginning of the program, just print out a prompt, greater than sign. Wait for the user to type in a command. Okay, and then they'll type in a command, hit an enter, and parse the command to see if it's one of these 5 commands: I number, P, S number, D number, or X. Okay, and then do the things that we just said. If you're inserting, try to insert the number, say either success, already in the list, or out of space. P can't really get an error message, just go ahead and print the entry in the list separated by spaces. If the list is empty, just, don't print anything. S number searches for a number, say found or not found. D number says success or no, not found, and X exits. Anything else, print out a short synopsis of what the commands are, right? Just remind the user how to use them. Don't delete all their files or shut down their machine or something. Okay, and again, you can catch errors like I not an integer or I without an argument. Don't worry about, ridiculous things like that, because I won't test that. All right, so deliverables, definitely all of the functions plus the main program, okay, whether it's one file, 2 files, or multiple files. I need all of those pieces of source code, okay. Got to have a lot of comments in your code. Got to have your name in your code, somewhere in your code. And for functions, right, when you write these functions, you should get in the habit of putting some comments in the beginning of the function that says, what does this function do? What are the inputs? What are the outputs? What are the side effects? Anything weird that you should know. Don't ever call delete unless you're sure the node is in the list. Because maybe your delete function doesn't do that search. Maybe it does, right? So have a block of comments before each function. Have a big block of comments in the beginning of your main program with your name, the class, the date, all that kind of stuff. And have comments on your code lines, right? Anytime you're doing something that's not 100% obvious, / few words saying what you're doing on that line of code. And then make a makefile. Okay, so we'll go through makefiles tomorrow. We'll do a refresh on that. Put it all into a tar file, upload it to Canvas. Okay, there's some how-tos on Canvas, but if you're not sure how to go from the Linux server to Canvas, come and ask me and I'll tell you. But you can use like WinSCP if you're on Windows, or you can just use SCP if you're on Linux or Mac. All right, so that's your deliverables. I'm going to make notes of all these things I'm promising to tell you. So there's some support code in here that I will talk about tomorrow, but let's go back to Let's just take a look at this really quickly. So if you want to use pointers, well, you don't want to, but if I decide to pass the address of my variable, then down here I simply say my argument is a pointer to my structure. And instead of A, I use star A. And I'll give you an embellishment on this tomorrow. Ooh. Prototypes. So my function takes a pointer to a struct name. Okay, so since the functions in PA1 require pointers to structures, right, when you pass your structure, you're going to use an ampersand in the front. Oh, never mind, I'm lying to you. Forget the last 1 minute. Never mind. Yeah, what's happening here is you're getting an array of struct nodes. That's why it's a pointer. So we're not passing an address of a struct node per se. We're passing an array. All right, so forget what I just said about the ampersands. No ampersands, still PA2. All right. So two other routines I want you to write, and these will be useful to you, but I also want you to write them because you're going to need to use them in PA2. One is called getNode, and the other is called releaseNode. Okay, what getNode does, it takes an array of struct nodes, and it searches through to find the first entry that has a valid field equal to 0. Okay, so it starts searching through your array until it finds an entry where valid is equal to 0. In other words, it's looking for an open spot, an entry in this array that's not in use. When it finds that, it does the following. It sets the valid flag to 1, and then it returns the index. So anytime you want to find a new spot in your array that you can use, the way to do it is to call getNode. Okay, and getNode will update the valid flag and tell you the index that's available. If you're out of space, getNode should return myNull, right, which we know is -1. So when you say getNode, check to see if it returned -1. If it did, there's no space left in the array. And then releaseNode does the opposite. You give it the array of struct nodes and the number, the index of the node you want to release, and all it does is clear the valid flag. Set it to a 0, and it basically makes that block free again. So in your insert delete functions, don't do these things directly. Call getNode, call releaseNode. Make sense? All right. So we got through all of this. So think about that. Ask questions tomorrow. Otherwise, I will do a refresher on makefiles, and then I want to look more at, take another look at building a linked list out of an array of these struct nodes, and start looking at some of the code that we can use.